Hello, everyone. Welcome to the 9th webinar in the Joint Tran-SET webinar series, which will cover a variety of research projects related to the future impacts of connected and automated vehicle applications from 3 quite different perspectives. So today we will have 3 15 to 20-minute presentations. First, Dr. Hani Hassan will go over the impacts of track platooning on transportation infrastructure. After that, Dr. Samer Dessouky will discuss an experimental and numerical assessment of CAV impact on flexible pavements. And finally, Dr. Mishra will provide a comprehensive overview of the adoption of highly automated vehicle technologies by individuals and organizations. So we will save the questions until the end of the 3 presentations for a 15-minute group Q&A. And you can type your question anytime throughout the session. So first, you will have to press on the Q&A button. After that, you will have to mark on send anonymously, and finally you will type your question in the box. Without further ado, I will introduce our first speaker, Dr. Hani Hassan. Dr. Hani Hassan is an assistant professor of transportation engineering at the Department of Civil and Environmental Engineering at Louisiana State University. His research interests include traffic safety, intelligent transportation systems, emerging technologies in transportation, and drivers' behavior. Dr. Hassan is currently serving as a member of the TRB Committee on User Information Systems. He is also a member and the paper review coordinator of the TRB Committee on Intelligent Transportation Systems. Dr. Hassan, I will turn it over to you now.
All right. You see my screen now?
Yeah, we can see your screen and we can hear you.
Okay, so good afternoon, everyone. This is Hani Hassan. It's a pleasure to give this presentation today. And the topic of my presentation will be about the impact of track platooning on transportation infrastructure. First of all, I would like to talk about the research team. Our research team in this project include Dr. Samer Dessouky from University of Texas at San Antonio and Dr. Ali Reza Talib from University of Illinois. In addition, we have several graduate students that are assisting us in this project. This is the outline of my presentation. First, I will discuss the background to explain the research motivation. Then I will discuss the project objective and methodology. Then in the remaining part of my presentation, I will talk about the current activity that we are doing related to corridor and network level analysis. Then at the end, I will conclude my presentation by explaining our next steps. So starting with background, as you know, it is very critical to provide efficient and safe movement of freight and for the economy of U.S. states, especially in the South region, in Region 6, that include Arkansas, Louisiana, New Mexico, Oklahoma, and Texas, where there are several largest freight distribution hubs. In addition, based on that, most valuable truck corridors are located in this region. As shown in these 2 figures, and according to a freight forecast study that was published by Federal Highway Administration in 2016, the total domestic freight flow tonnage will grow by about 6 billion tons over the forecast period from 2012 to 2005. and this represents an increase of over 40%. In addition, over the entire period of this forecast, the total real values of domestic freight flows will grow up from about $40 trillion in 2012 to about $22 trillion in 2045. And this representing about 60% increase. These two figures show the truck flows on our U.S. national highway system in 2012 and their forecast for the year 2045. As you can see from these figures, it's clear that there will be a significant increase of the truck flows on the U.S. national highway system over the coming 25 years. Unfortunately, there are several challenges that will affect the effect of freight movement, including having high fuel and labor cost, having vehicular emissions, and having problems related to traffic safety, resulting mainly from the truck driver's error. For example, due to the need to drive for long distance and extended time. Fortunately, emerging vehicle technology such as connected and automated vehicle, CAVs, can help in minimizing these challenges. And one CAV application of particular interest to the freight industry is the truck platooning. As you know, truck platooning consists of a number of trucks equipped with connected and autonomous vehicle technology that closely flow one another in a platoon. Considering recent studies, we expect that truck platooning may result in significant changes in freight shipment operation, and this can create a great potential in addressing current challenges facing freight movement. In addition, it's expected that truck platooning can help in reducing consumption, emission, labor cost. Also, it may provide traffic safety and traffic flow improvement. On the other hand, truck platooning may accelerate the pavement damage due to its greater weight concentration. So considering the literature review, very little studies concentrated on the safety aspects of truck platooning as well as the impact on pavement. Indeed, there are a number of research issues that need to be considered, such as the effect of shorter headways on the capacity or improved traffic flow stability, and the potential negative effect of truck platooning, such as blocking at ramps. So in our analysis, we will give a special focus on this safety aspect and the impact of truck platooning on pavement to fill this gap in the literature. Based on that, we have developed an integrated approach to achieve this objective. In this project, we have three main objectives. The first one is to examine the operational and environmental impact of truck platooning on our U.S. highways. And we will do that series of modeling case studies in Region 6. The operational and environmental impact of various truck platooning implementation, configuration, and assumption will be quantified at both the corridor and network level. Then the second objective is to explore the impact of truck platooning on pavement. And Dr. Samer Dosouky, our second presenter, will talk about this second objective in more detail in his presentation. And after that, our third objective is to conduct a feasibility study and provide some recommendation. So we will develop an economic analysis comparing the potential operational and environmental benefit of truck platooning with the potential increase in maintenance cost associated with the heavier pavement loads and the loading configuration of truck platooning. I will start discussing first our effort related to the corridor level analysis. The data set used in our analysis was obtained from the National Performance Management Research Data Set, NPMRDS. And this data set contains GIS shape files of TMS segment, which includes the average annual daily traffic data. And this data set actually provides massive daily data from 2011 to 2020 for 24 hours period with a 10, 15, and 60-minute interval. For every record, it includes speed, historical average speed, reference speed, travel time, and data density values. Based on that, we can select the data using TMS code and download it even in CSV format. The output provides mainly two files, one containing the speed and the travel time data, and they're containing the TMS segment data. In addition, speed travel time file includes data related to speed, historical average speed, travel time, and density value for every time period. The TMS segment, like the number of through lanes and the average annual daily traffic. Also from the Capital Region Planning Commission, CRPS, we have obtained valuable data that includes GIS shape files of TMS segment for Baton Rouge segment with AADT data. Based on that, we have selected a freeway segment with diverging and merging section on I-10 road in Louisiana, which is a heavily utilized truck corridor situated in Region 6. We have collected the GIS shape files of the segment that was used later to create the roadway network in VSIM software. So this figure and the following one shows a VSIM roadway network that was developed. And to model the truck platooning in VSIM, we have integrated Python with VSIM to code the connected and autonomous vehicle platform. And we are currently preparing some or different platooning scenario to be utilized or to be examined in VSIM, as we're gonna discuss in the following slide. As you know, to examine the impacts of truck platooning on traffic operation and safety, there are several factors that need to be considered. These factors include platoon size, how many trucks in the platoon. It includes also the inter-platoon distance, the intra-platoon distance, like the headways between trucks. Also, market penetration rates is one of the important factors to be considered, which represent the percentage of automated vehicles in the traffic stream. And also the time of analysis, like peak and off-peak hour, is one of the important factors that we need. It needs to be considered. So considering this factor, the result of experimental design showed that there are a total of 144 simulation scenarios that need to be examined. However, using fractional factorial design method, the number of simulation scenario can be reduced to only 36 scenario, as shown in these two tables. So as shown in the tables, we will have one base or reference scenario for peak hour and one base or reference scenario for off-peak hour. Then we will have different scenarios considering different values for the market penetration ratio, platoon size, intra-platoon distance, and headways. There are several surrogate measures that were considered in our analysis to align the microscopic analysis with the project objective. So to assess the operational impact of track platooning, we considered surrogate measures such as the total network delay, time to merge and diverge. In addition to investigate the environmental impacts, we will use a total emission of CO2, NOx, and PM10. Finally, time integrated time to collision will be used as a surrogate measure to assess the impacts of truck platooning on traffic safety. Regarding the expected result from our analysis in this part, it is expected that the truck platooning will show or will help in reducing the emission of CO2, NOx, and PM10. However, we expect that traffic flow at especially at complex traffic areas such as merging and diverging sections of the highways might be impacted. This effect will be significant with a higher penetration rate of truck platoons. In addition, truck platooning may have a negative impact on traffic safety, especially at merging and diverging areas. However, we will strive to identify the optimal truck platooning size or a strategy that can have a positive impact on the operational, environmental, and safety aspect of highway and can help in reducing stress on pavement. Now I will talk about the network level analysis that we have done so far. One of the objectives of this research is to assess the mesoscopic level impact of truck platooning on traffic congestion. As you know, mesoscopic models combine the properties of both microscopic and macroscopic simulation models. And in this regard, mesoscopic models might provide less accuracy than the microsimulation tools, but they are superior to the typical planning analysis techniques. So accurate modeling of the impact of truck platooning at the mesoscopic level requires accurate speed density diagrams. And these speed density diagrams can be obtained using two sources from the microscopic simulation. However, it might be inaccurate without proper calibration. Also, it can be obtained from the real-world data. However, it's mostly unavailable. So we have utilized unmanned aerial vehicle UAVs to collect data for I-35 in Austin, Texas. The collected data then was utilized to calibrate our microscopic simulation models. Then the calibrated microscopic simulation was utilized to develop speed density and the flow density diagram for different platooning scenarios. Then vehicle trajectory data was collected from a segment of I-35 in Austin. Based on that, an automated deep learning based vehicle detection algorithm was developed to analyze the UAV data. Once the vehicle are detected, a tracking based algorithm was developed to create the individual vehicle trajectory data. Such data was extracted for all vehicles traveling in the segment of interest. Then this data includes the location, speed, and acceleration of all vehicles. It should be noted that the extracted vehicle trajectory data is not perfect, and the algorithm can result in unrealistic movement. Therefore, Kalman filter was utilized to ensure accurate tracking of the vehicle in our scenarios. The genetic algorithm is based on the calibration approach introduced by Hamidar and Mahmasani, and several assumptions should be made to implement this genetic algorithm. For example, the parameter of car following lane changing model are initiated to random numbers. Then each set of these parameters is called a chromosome. The fitness of each chromosome is determined using the error function. Except for the chromosome with the lower error value, every other chromosome will be evolved through crossover and mutation. The process is terminated then once a minimum error threshold is achieved by the best chromosome. Our focus in the analysis was given on the interaction between human driver and automated vehicle, especially focused on three main factors. First, a human driver following an automated vehicle, a human driver changing lane into the gap between vehicle in a platoon, and on the automated vehicle or a platoon of automated vehicle changing lane in front of a human driven vehicle. This slide shows the initial results that we have obtained so far. So this 5 figure shows a relationship between density and the flow. The 3 figures on the top show the relationship between density and the flow at 10% market penetration, or 10% vehicle, automated vehicle, 10% truck at 3 cases. No platooning, 2 vehicle per platoon, and 10 vehicle per platoon. However, the 2 figures at the bottom show the relationship between flow and density at 60% automated vehicle and 10% truck at 2 cases, no platooning and at 10 vehicle per platoon. The results show that even at low market penetration rate, platooning can significantly reduce the scatter and increase the traffic flow or throughput. However, once the platoon size increases, the lane changing ability reduces significantly. I will finish my presentation by explaining our next steps. And the next step, we plan to complete our corridor level analysis, our network level analysis, and to complete the analysis related to the impact of truck platooning on pavement. Then, utilizing all this result, an economic analysis will be conducted to compare the operational and environmental benefit of traffic platooning with the potential increase in maintenance cost due to the heavier pavement loads and loading configuration of truck platooning. So this was my presentation. Thank you so much for your attention, and I will be happy to answer your question at the end of this meeting. Thank you. Dr. Mu'min?
Yes, I can hear you. Thank you very much, Dr. Hassan. That was very informative and interesting, and I can see many questions, and we'll be sure to answer all of these questions and at the end of the 3 presentations. So now I will introduce our second speaker, Dr. Samer Dessouky. Dr. Samer is a professor in civil and environmental engineering at the University of Texas, San Antonio. He has more than 20 years of experience in pavement materials analysis, sustainability, and traffic safety. He is a former chair of the Bituminous Committee of ASC Construction Institute, associate director of Tran-SET UTC, and associate editor of ASCE Journal of Materials. He is a professional engineer in Ohio and Texas. Dr. Samer, I will turn it to you now.
All right. Good afternoon, everybody. And just want to make sure you can hear me well and you can see my slide.
Yeah, we can hear you and we can see your slides.
Okay, very good. It's my pleasure to be presenting today in the Tran-SET webinar. I'm glad to be here and I welcome everybody. Today, I complement the work that Dr. Hani Hassan presented in the first presentation today to talk about the impact of the connected autonomous vehicles on flexible pavement, with the focus primarily on the heavy vehicle platooning. First, I wanted to acknowledge my PhD students, Sayed Yasha Shirazi, for really doing primarily most of the work. As Dr. Hani just talked about the platooning technology and how this is an upcoming potential technology that potentially is going to help out with mobility, safety, and environmental issues that we face currently in our infrastructure highway system. And hopefully we could solve some of the congestions and the safety issues that we have. And we're aiming at a self-driving technology that currently being developed and deployed will help with all those issues. Let's see here. So the fact that going through the literature, we found this technology is really going to provide a lot of benefits, but when it comes down to find out how this technology will impact pavements, we couldn't really find much. That's why we propose in this project with LSU to come up with a methodology to assess how this heavy vehicle platooning HVP is going to impact flexible pavement. So the project objectives here is first, we wanted to learn from the literature and others who have done a similar technology, whether on a lab scale, whether on a controlled testing scale, whether using accelerated testing facility, if we could learn how heavy vehicle platooning could impact pavement performance. And hopefully from this literature, we could teach ourselves what really is missing and what we really need to do in order to provide a complete picture on the impact of heavy vehicle platooning on the pavement performance. Learning from this is guidance to the next step, which is developing a finite element modeling to help estimate the structure and the performance impact of HVP on highway pavement structures. The fact that we don't have an actual technology running in our highway systems, there might be some preliminary technology developed in Europe, but the fact that we don't have it here, so we find that the best approach to do that is to go and run numerical assessment using finite element modeling. So I'm going to start first with some of the work that I personally have done at University of Illinois on using an experimental study that we found we could learn a lot from to understand how truck loading on the pavement on a controlled environment could help us to learn a lot about how the pavement will impact, what we could do for the pavement structure to support such loading, and what we could do to optimize the structure to sustain such heavy loading that's running over certain area in the pavement over and over. So we have here a pavement structure that was completely constructed from scratch. And basically it runs through a 3-inch of hot mix asphalt on the top over several different layers of base structures in different thicknesses from 8-inch to 12 to 18. And there is a choice of having only one section to have a little bit of more hot mix asphalt thickness in order to see the impact of increasing the pavement thickness. And this was structured basically to run the test on 3 different sections at a time. So there was a testing done here on an A sections, and then a 1 testing done on the B and C section, and then 1 separate testing on the D sections. The idea from this testing experiment is primarily to analyze the impact of a geogrid, the impact of truck loading on pavement structure, but we found that we could learn a lot to develop finite element modeling based on what we learned from the experiment on this project. So basically what we intended to do is to instrument the pavement with the several instruments just to provide the structure data and the stress and strain responses at different layers in the pavement structure to allow us to analyze the pavement performance and develop numerical models that can eventually provide future performance of the pavement over time if you wanted to expand the testing loads on the pavement. So we introduced several instruments like strain gauges at the bottom of the hot mix asphalt, LVDTs at the base and the subgrade level, and pressure cells right under the base layers, just to make sure that we're collecting stresses and strains all over the pavement sections. And this is a snapshot of those instruments that were installed at different layers in the pavement, because really what you really wanted to do is how the pavement responses to the loading impacted on the top surface. And from there, you could come up with a complete set of responses that help with numerical simulation. So we took advantage of the current accelerated testing facility at University of Illinois to run a full testing on the pavement section that was presented previously. And as I said, it was done on 3 sites at a time because the span of the facility was limited. So it had to be run at different sections at a time. But we had the opportunity to run the accelerated facility, which you can really link this to a platooning-like testing by having this configuration of dual truck tires running over the pavement back and forth at a controlled environment, from loading, from tire pressure, from speeds at different offsets or wandering throughout the pavement from the center line of the pavement. And you can run that as much as you want it until you feel justified that the pavement is already damaged. You have the option also to change the tire configuration from dual tire to wide base tire. So this is all available to run on the pavement section when it comes to accelerated facility. The fact that you are limited with the space and with the speed, you cannot really go to model this on a highway speed. That was the shortcoming that you expect. In addition to that, this is a controlled environment testing, but when it comes to temperature, it now varies the pavement responses. So you really have to go to the material properties to adjust to the temperature all the time, just to have a consistent way to put all the sections to compare them against each other consistently. But we said this is a good experiment that we could learn from to help with our analysis with heavy vehicle platooning on highway system. So this is some of the results that you could expect. If we allow a heavy vehicle platooning really to run over the same exact spot using the current technology, here is what you're gonna run through. So for example, this is one of the sections, and here is before the testing start, and you can see there is a tire imprint here at the center of the pavement. But eventually, if you keep that tire running over and over, you accumulate rutting right at the center. And that rutting could really becomes much more than what's allowed in the pavement structure. So here you can see after 30,000 passes of the truck tires, which is done exactly over the same spot, have really results on a massive rutting, which is absolutely exceeding what's allowed in a pavement structure. And this is a structure that has a 3-inch of hot mix, 12-inch of base over a subgrade. Really, it has nothing to be close to a highway structure layers, but it just gives an idea on what could happen eventually if that 30,000s become 3 millions or even more. So eventually this rutting is going to accumulate. And here is, if you're looking into 3 different structures, from one that it's actually 312, and then another 312 with a supporting layer of a geogrids. But here is the 5-inch hot mix asphalt on top over the same base layers. You can see how a 2 inches of asphalt layer have reduced the accumulated rutting from 48 millimeter down to 7 millimeter, a huge impact for just investing on increasing the hot mix asphalt layer. It just tells you how important when you look into where you can beef your pavement structure to eliminate some of those distresses in pavement, where you could invest the most. It was clearly shown here that a hot mix asphalt could have a huge impact to reduce the rutting. Again, there's still a 7 millimeter of rutting, kind of a 1/4 inch after 50,000 passes. So that's something can also be accumulated further with 10, 100 times of passes, especially if you're talking about interstate highway system. This is a snapshot for how the cracking been initiated and propagated throughout that central part of the pavement. You can see lateral cracks across that eventually have leading up to some separations on that portions of the pavement that makes it complete failure due to the separation. The fact that this was not visible initially and at the end of the experiment after 50,000 cycle for the one with the thick asphalt pavement, but it tells that eventually it's an accumulation of shear cracking and transverse cracking across, longitudinal and transverse cracking across the wheel loading area. So putting together all the passes and with the responses, for example, from the pressure cells at the subgrade level, you can see that the pressure is accumulating or increasing as the number of passes is increasing, which tells there is already damage that happens at the layers underneath the wheeling, the loading wheel path. And that depends on the thickness that you have, how fast that damage happens, depends on the structural layers and the strength of the material that you have. But eventually, the control section turns out to be the one that have been increased with a higher failure rate than the others, with a little bit of a less rate of failure for the one with a geogrid layer, and absolutely a very minimal failure or reduced failure completely when it comes to the one with thicker hot mix asphalt. So going over this experiment and reading about the same who have done similar work on platooning and what they learned from it from the literature, we found that there is two issues that come here. First is the limited wandering for not allowing the trucks to really to offset their movement across the lane and make sure that that load keep distributing across the lane to some extent is a huge problem. Second, the less headway distance between the vehicles could not allow the pavement the time to some extent to recover some of those deformation that happens after the truck loading or the heavy vehicle runs over it. So that means we expect to see an accelerated failure on the lane dedicated for the platooning if those items are not addressed well. There is another issue that have been addressed in the literature as well in terms of overloading, the fact that you would dedicate a lane for platooning that could provide some kind of a comfort zone for truck drivers to overload their trucks, which could lead to a 20 to 50% reduction in the pavement fatigue life over time, as documented in the literature. That's another issue. Although there is numerous studies that conducted to evaluate various aspects of heavy vehicle platooning, the specific topic that addressed pavement condition was not there yet. So we elected to run a finite element, three-dimensional finite element models, and collecting as many information as possible from an existing highway pavement structure in Texas. And after Dr. Hani Hassan, you can tell that we all agree to use Interstate Highway 35, one of the major corridors in Texas that runs from Mexico all the way to North America, and running through three major cities in Texas: San Antonio, Austin, and Dallas. And we're fortunate that we have all this information. You can see it here in the flowchart collected with our colleague at Texas A&M, Dr. Lubinda Walobita, who was really providing with a lot of information from traffic, from materials, from seasonal temperature variations as part of a TexDOT project he's conducting to build a database. So we agreed to use that because we have lots of information about that highway system that allow us to develop the model. And here is the pavement structures. It's about more than 2 feet in thickness, and that includes 6 inches of base layer here, but several layers of asphalt that keep adding up. It's a massive corridor with a massive traffic daily, including heavy vehicles that runs every day. And that's how these structure look like. This is no way close to what I presented earlier, but it just gives you an idea of what kind of traffic we expect here. So we have all the information for those layers, and we were able to develop the three-dimensional finite element based on this information. And we were able also to use some of the material properties and the dynamic modulus data that was collected from those layers, as well as part of the database that was developed under a TexDOT grant. So we have also the material properties, specifically the master care for those layers, that allow us really to put all those layers under one temperature reference to allow us to run this at different seasons, but combine that to collect measurements at specific temperature to be consistent if we run the traffic all over the year on our model. This is the traffic distributions of truck loading on the Interstate Highway 35, and you can see that the red part of it, where most of the truck loading is located, And you can see that some of those steering wheels, non-steering wheels, tandem and tridem and quad, you can see exactly where you want to put your focus on when you develop the model. So that will give us an idea what kind of tire configuration we could put in our models. Here is a simulation of the three-dimensional model with the moving wheel on top. In fact, that will allow, by running this wheel, to get the responses at different layers throughout the pavement structure. So what Yasha have done is to develop a 100-meter length model to run this at some point to match the highway speed without corrupting the models because of some convergent issues we initially had. And we provided some condensed mesh at the middle part of the pavement to improve accuracy for pavement responses. And we allow the wheel to roll over the center part of the model to simulate the HVP, the heavy vehicle platooning. Again, we have all the information that allow us to run this, and is it just a time to collect the measurements? Again, some of the responses from the pavement to validate and calibrate the model is also available based on some of the testing that was done and some of the measurements of cracking and rutting that was collected as part of the database. So we could also calibrate that models, and that allow us now to integrate all the combinations of platooning that we could introduce to the model based on number of passes, speeds, offsets, tire pressures. We can combine all that now in one single lane, and you can accumulate the responses in terms of rutting and fatigue cracking to see how platooning could impact the pavement performance. So here is an example of a horizontal strain at the bottom of asphalt concrete layer. You can see that as far as you allow this to be running over the center, you get the maximum response right under, but when you have an offset, you really have a reduced response of the strain. So the fact that when you allow that wander to be taking place in the pavement, you are reducing or you are moving that peak across certain area in the pavement, making the pavement to survive at some point, not to have that peak concentrated at one point all the time that cause an accelerated damage. So that also is visible when you look into the vertical stresses at the bottom of the asphalt layers all the way to the subgrade. I know we have about 24 inch of asphalt layers, but at the end of the day, you still have some pressure that at the subgrade level, giving the massive loading on the Interstate Highway 35 on a daily basis. So again, wandering and offsets that can be implemented within the platooning technology could allow to offset that damage and minimize the failure in the pavement if it is not done correctly. So what we came up with is at this point is we are running several simulations to see how we can learn from running different combinations of platooning given the current data that we have, but instead of running them at different lanes from current operations, we are combining all these operations to be at one single lane to simulate the concept of the platooning. So all this combination now is going to be dedicated to one lane, and we put that all in one finite element model over a single lane to run all those operations and see how that will accelerate the pavement layers versus a scenario where there's a control scenario if that traffic level is distributed among different lanes in the pavement. So we consider conventional operations to be the control, and we consider the platooning to be the case study, and we can compare the damage accelerations from both cases and see what we expect to get from that technology. So based on our strain values responses at the bottom of the asphalt layer, we noticed that a 5-inch offset could decrease the strain magnitude about 25%, and that eventually could improve the fatigue life 3.5 times. That's versus if you keep running them over the same spot over and over. Since this could be computerized to be running exactly following the lead track. Another simulation from the vertical stresses have suggested that if there is an 8 to 16 inch offset, that could reduce the vertical stresses from 62 to 48% respectively. Again, that's expected the damage when it comes to the rutting at the subgrade level. And that could help with reducing rutting about 1.6 times. So that's where really a just brief conclusion on what we have. There is still more cases to run on the models. It just, since we have a 100-meter model, it takes forever to run each case, but we are really putting together all the scenarios and all the cases to collect the stress and strain and the deflections, and putting together all the overloading conditions that could be possibly leading to more damage acceleration in the pavement layers. What we learn from it is the potential policies and regulation needed to overcome the overloading situations and the truck width limits by providing results on what could happen when you have overloading, what could happen if you have lower and smaller headways, and what would happen when you have fixed wandering or no offsets in the movement of the platooning. And that could lead us to provide maybe alternative mix designs, or maybe the choice of using PCC exclusively for the platooning lane if needed, based on what we could do to minimize that failure. With that, that will conclude my presentation, and I'm happy to take your questions by the end.
Okay, thank you very much, Dr. Samer. That was excellent. We really appreciate it. So now, I will introduce our last presenter, Dr. Mishra. Dr. Mishra is Associate Professor of Civil Engineering and the co-editor of FedEx Institute of Technology's Smart City Research Cluster at the University of Memphis. His research interests include traffic demand modeling, network investment, decision-making, transportation planning, economics, and the impact of disruptive technological innovations on transportation. He is involved with a number of national and state transportation projects from U.S. Department of Transportation, Federal Highway Administration, Tennessee DOT, Maryland State Highway Administration, Maryland DOT, and Michigan DOT. He has published over 160 articles in peer-reviewed journals and conference proceedings. Dr. Mishra is a Vice Chair of the Transportation Economics Committee and Freight Economics and Regulation Committee of the TRB of the National Academy of Sciences, ASCE, Institute of Transportation Engineers, and Association of Unmanned Vehicle System Internationals. Dr. Mishra, I will turn it over to you now.
All right, good afternoon. Can you hear me okay?
Yeah, I can hear you, and I can see your slides.
Okay, thank you so much.
You're welcome.
Good afternoon, everyone. Glad to be here and pleasure speaking to all of you this afternoon on a topic that we have been working on it for about last 3 to 4 years. So before I begin the presentation, I would like to thank my colleague, Dr. Mihalis Golias. He and I worked closely on a number of projects. Especially on this project, I'd like to thank 2 of our terrific graduate students. Both of them are doctoral students. One is Ishan Sharma, and the next is Jesse Simpson. It's most of their work that we'll see in today's presentation. So the way we have organized today's presentation is on 2 parts. So we'll look into adoption of highly automated vehicle technologies by individuals and then by organizations. So first we'll look into individuals, and then for organizations, and then for each we'll look into what is the background and what is the motivation that essentially told us that we need to do research in this direction, and then what approach we followed, and then what are some of our key findings, followed by conclusion. So first we look into individual adoption of highly automated technology. When we see that we have been hearing about connected autonomous vehicles or highly automated vehicular technologies for a few years. And we all agree that those have greater potential in terms of providing benefits to us. In terms of whether owning such a vehicle or using it for our purpose, either in a shared fashion or using in the form of a public transportation per se, those are mixed opinions in terms of how do we want to adopt such type of technologies. The main questions for transportation planners remain as that, how do we identify demand for such type of technologies? Those are disruptive and those are upcoming, even though in the early stages. So when we look into literature, we see majority of studies, and most of them revolve around modeling of perceptions or attitudinal preferences in terms of adoption towards such technologies. So many studies would focus in terms of just using the sales data. Some use what people have said in various types of surveys. But what we know is that such type of studies generally would not be able to capture the adoption element, because adoption element, people, when they make a decision based on a technology that they have not seen, is to do with not only what they decide by themselves, but also what do they receive information from their peers, meaning who are they connected to in their social network and how they're influenced by others in their social network, either at work or at home or in their friend circle. So considering that, sometimes our traditional analysis of choice models or the techniques that we typically utilize, kind of we put a question mark, are they fit enough for us to analyze impact of such technologies in terms of adoption, meaning when we consider the demand. So we see that many states welcome CAVs or highly automated technologies. Those are in legislations. So even Department of Transportation, they're thinking about how do we plan for infrastructure. So before planning for infrastructure, we need to understand how do we model demand. So what we see in this slide is various types of figures. We're not looking for a self or driverless car or self-driving car, but we see various level of automation being available. And some of the vehicular technologies may require information from the infrastructure as well. And we would like to know who are the people or who are the individuals, or what would be the likely demand of such type of technologies in the future. So before proceeding, we thought, let us see that in transportation, we're seeing that disruptive technologies are coming into our world recently, but there has been many disruptive technologies that we have seen in generations. So many of them look like the traditional S-curve. What we see in this figure is when an innovation started, and the year from that, or the time from that period when the innovation started, and how much time it took to reach to higher degree of penetration, let's say 100%. So what we see that number of innovations such as television, internet, automobile, they reach to 100% penetration very quickly. Whereas other innovations such as digital camera or VCR, for example, they did not even reach to 100%. Some of them stopped at 50%, others 60, 70%, because other type of innovations came in and disrupted their progress. So at least we know that in transportation, CAVs, for example, or highly automated technologies, when we look for an adoption curve, probably it would look something in one of these type of S curves. So what will it look like at this point of time? We don't know, but we need to explore. But this is something to understand that what has been happened over other innovations. Looking into literature, what we see is that in terms of specifically talking about CAVs, we see that people having higher education levels or gender such as main, or using word of mouth, positive word of mouth, or things such as CAVs will have lower insurance prices, people leading a tech-savvy lifestyle, or even people not able to drive right now, but will have access to a vehicle that is going to drive by itself, are some of the positive impacts that motivates people to essentially adopt such a type of technology. Whereas people are concerned in terms of the safety aspects, such as what about the vehicle will lose control, or things such as what are the liability consequences, what about the operation and maintenance costs, because the highly automated technologies will have also higher costs associated with it, or people who are passionate about driving would not welcome such type of technologies if it's going to drive by itself. And people are also concerned about privacy of their own data, or if the vehicle will be hacked, or it will have cybersecurity issues. So these are some of the elements what we found from literature on people who have done various types of surveys on different parts of the world. But irrespective to that, what we see on the right-hand side, extreme right-hand side of this slide, is an adoption curve taken from Rogers, one of the founders of a technique called as diffusion of innovations, that looks as an S-curve and that categorizes 5 different types of adopters, such as innovators, who are just be the first category of people to try the innovation, about 2.5% of the overall population, and followed by some which are opinion leaders, meaning thereby they're just waiting for the innovators to take first and see how it goes, and then they will adopt thereafter. If for initial few years an innovation sees about 16% of diffusion, then the rate after that is very steep, meaning in the S-curve, the middle part, from about 16% till about 90%, that has been achieved in a very small time frame, followed by the very last portion, which are kind of the laggards, or people who are waiting or essentially love the current technology, are not ready to embrace. They will be the last ones, and they will look for essentially if they have to adapt, or they can even survive without the technology not being used, even the technology. So these are different types of segments of people. Even when we want to model them or find the demand, we need to consider these type of people as well in our analysis. So we looked into various types of diffusion of innovation technologies, such as initial aggregate methods, such as BAS model or other diffusion of innovation methods. What we found to be more interesting would be if we can capture each and every individual agent in the system and understand their behavior, that would be more impactful. So we looked into agent-based models to provide the most accurate information for such type of analysis. So the first part we wanted to understand is that how one social network impacts one's decision. So let us look into the figure that we have on this slide. So what we see is 3 types of agents. The colored blue says that it's an adopted agent. The green one is a potential adopter, not very sure right now. And the red one is a susceptible agent. So 2 things to find on this figure is that one is that there is a distance between 2 agents that represents how closely related they are. And the second is the thickness of their closeness, meaning is the strength of the connection very high or very low, or what is their strength? So the purpose of doing such type of analysis is to find out if a specific peer or a specific connection or specific way one is connected to another person, one individual is connected to another individual, is being affected, meaning there is a probability or likelihood that an adopted agent might influence a potential adopter, or a potential adopter might even affect a susceptible agent in the time to come. So those are the things that we wanted to study in the form of a social network. So before constructing a social network, we thought that the things that would impact would be to understand what are some of the barriers. 2 barriers of importance we looked into were psychological barriers and functional barriers. So in psychological barriers, meaning people are concerned about their traditions or norms, what is the type of image that is going to bring if they're going to adopt the innovation? Are there any social barriers that they need to overcome? Similarly, in terms of functional barrier, those are mostly related to the technology itself, thinking about whether the technology is sustainable enough or is it sound enough for one to switch from what one is currently using versus what one is coming in the future. And then we wanted to capture also what is the impact of media, such as advertisement, pre as well as post, pre-introduction of technology as well as post-introduction of technology, peer-to-peer communication in word of mouth, as well as what are the resistance to new innovation, and not to kind of isolate what is the impact of government regulation or policies if that impact one's likelihood of adopting a specific innovation. So with that, this is a very brief sketch of our methodology that we wanted to, or we implemented in our work, is that the first one that the agent-based model would be dependent on is perceptions or opinion of individuals who are in the study. So that has been captured in the adoption survey. And of course, the survey will not be 100%, meaning all the individuals would not respond to the survey. But we need to expand if we want to understand what is the potential demand in a city or in a region. So we want to understand each and everybody's opinion. So we need to construct a synthetic population out of the sample data we observed or we got from the study. And then we need to create the social network, what we saw in the previous slide. That is something we create in the network synthesis step, as well as the three important steps that being carried out actually for is the four submodels. Those are implemented in the ABM. Is the adoption submodel, meaning what are the components which people are concerned in terms of adoption, and communication, meaning how they communicate with their peers in their network, government regulations, as well as any type of processes that may need to be considered. And finally, we get some sort of adoption outcome, such as ready to adopt now, or wait and adopt, or defer and adopt later, or not adopt right now, or kind of reject the adoption. Those would be the outcomes which would come out of this analysis. So we have a paper on this on part C that has been published. So where we go deep into the methodological framework, which I'm omitting for this presentation for the lack of time. But I'll go to the data that we collected in terms of next steps. So we collected data on University of Memphis campus, on our campus, and about close to 3,000 employees and staff who have capability to purchase. So we did not include students because we assume that they don't have the purchasing capability of a vehicle. So only staff and faculty were reviewed, and about 13% of response rate with that. So some of the important things that came out of the survey was that people were information that they received from peers that they valued much. So the mean score of 5.5 out of a 7 scale states that, such as people depending on the media, on what they see on news channels, as well as other social platforms, they depend on that. They also depend on what they hear from car dealership. In terms of willingness to pay towards full automation, people are concerned about cost. If the cost is less on what they're currently paying, of 5,000 or less, then about 70% of individuals were ready to adopt, as long as it is safe and it is cheaper. So some important things that people valued were increased mobility, meaning people can drive, or the drive can vehicle themselves, or high automated technologies can help them in terms of driving, as well as loss of control. For example, people valued locks, that if the vehicle can take care of that, because number of crashes happen because of human errors. So if it can address that, then that would be very helpful. Since the survey was conducted in an academic environment, people are also valuable towards pollution, but that might not be the case in a general public survey. But these are some of the important features that we saw. When we construct the social network out of the survey data, then the network sees like this. So few important features. First, how do we construct a social network? It is based on a concept of homophily, which says that or a principle which indicates that the possibility that a pair of agents establish a connection which is a function of the geographical proximity and socio-demographic similarity. So we construct this social network based on 8-dimensional coordinate system. So those 8 dimensions include such as age, gender, race, employment type, income, and other features, which were important. Though we started with more number of attributes, but we finally settled on 8-dimensional coordinate system. So I will not go to the formula on this slide, but that shows how we computed the distance between 2 agents, I and J, and what is the strength of their communication. One important feature to see here is that the right side of the graph is very closely connected than the left side of the graph. So the right side of the graph, when we looked into who are the individuals on campus who are closely connected, that turned out to be especially people who are staff members, whereas the left-hand side are mostly like faculty members. So what happens that there is much more coordination among staff members in terms of the number of meetings that they attend, the way type of that they're connected with each other, rather than individual departments where function kind of differently from each other, in which individual faculty essentially work in their own ways. So we see the kind of strong coordination among staff members rather than faculty members, which we kind of found intuitive in the study. Looking into results, what we see here is that the first figure we see on the left-hand side is the sales price reduction. So what currently people pay versus if we reduce the price by 5% till 20% with 5% of increment. If the price reduction is going to be 5% on what people pay right now, then the market penetration will be around 10 to 15%, even in a 25-year period. However, meaning I would take it back, not what they're currently paying versus what is the projected cost of the CAVs right now. So that is what is the cost is based on. So if the cost of the CAVs is going to be 20% less than what is currently being projected, then the penetration rate would be somewhere close to 90% in about 30-year time period. What we see on the right-hand side, also on the left-hand side before I finish, is that there are 3 curves here. One is the mean, and another is the lower and upper bound at 95% confidence interval. The reason we don't see is that the model is accurate enough not to have a bigger bandwidth of lower and upper confidence intervals. The right-hand side figure essentially shows advertisement impact, and this is post-introduction of the technology advertise impact. If there is no marketing or very low type of marketing, then that would not have a larger impact in terms of adoption. So very low marketing would result something like about 8% of penetration rate. However, if media advertisement is going to be at least somewhat moderate, then we might see the impact going from somewhere close to 50%. There is no substantial difference in terms of when advertisement impact would be kind of high or very high versus average. As long as media advertisement or advertisement impact is average, that is good enough to reach out the advantage of technology to the individuals. Then we see the negative side of adoption is that what happens if there are number of CAV users who are dissatisfied. So in those cases, they're going to spread negative word of mouth. So let's look into the dissatisfied CAV users. So this is something we take as the price is going to be 10% lower than what is currently being projected. And what we see is that number of dissatisfied users kind of still remain around 4% or so over time. Even though one is remain dissatisfied, it may spread the word, and the number of dissatisfied users do not essentially increase a lot if the technology still tends to provide similar type of advertisements over the years. In terms of negative word of mouth spreaders, if one dissatisfied user is going to spread negative word of mouth, then that percentage might go on increasing over the time period of 25 years, but that percentage also will kind of saturate around 4% or so. So the impact of negative word of mouth spreaders is not huge in terms of what the data that we are analyzing here. But nonetheless, we essentially found out a method which we can incorporate to identify demand for CAVs. So somebody will ask, okay, how reliable are these methods on what we are presenting? So what we did for that was that we collected additional data in a second round, in which all the responders who responded to the first round of survey were excluded. And then with a newer data set, we validated the model in terms of how the demand is going to be. And what we see a lot of similarity in terms of what the model presented versus what we forecasted, meaning observed as well as the predicted data. So that's what is what we found out. There are more in this paper, which is on the right-hand side that we present, but for the lack of time, I would kind of stop here in terms of use of agent-based models for individual adoption. What we have recently done is also used integrated choice and latent variable modeling framework called as ICLV, which many of you are familiar. And if you are not, then it consists of two steps. One is a structural equation modeling part, that is part one, and the second one is a discrete choice modeling part. So the structural equation modeling part essentially captures the perceptions and resistances, and whereas the discrete choice modeling part essentially considers the random utility theory and tells us what is the likelihood or the probability that an individual is going to adopt CAVs. So the general framework is given here on the slide, and I would kind of move quickly here because of lack of time. So the first part represents the structural equation modeling part, and the second part presents the discrete choice modeling part. But the main goal here is to find out what are the factors in terms of attitudes, perception, resistances, as well as social values. But the important part is, can we find out the latent variables present in the model? So what we see in the next slide is the left-hand side, which is the structural equation modeling part, which captures 4 important latent variables. So one is social image, that is really concerned with how people are connected to each other at work and not at work, and if purchasing the vehicle will improve their status. In terms of benefits, whether the vehicle is going to generate kind of less pollution or whether it's going to provide more mobility, like that for barriers and CAV purchase. So we found out, so our cutoff value here was 0.4. So any value which is 0.4 is presented here. The right-hand side figure essentially provides the whole methodology in terms of how we identify the structural equation or the latent variables and how it is connected to the discrete choice model. So all observed variables, what we see is in the form of squares. On observed variables essentially is in kind of oval shape, and the coefficients that we estimate or we are planning to estimate are in gray color format, and the relationships are present in arrows, that is in the legend. So I will not spend again much time here, but we'll go to the results. What we see here is that what is the likelihood towards adoption and what are some of the barriers? So first, looking into what are the factors that is contributing less likely to adopt. One is the race in terms of here in our population, we see that individuals with white ethnicity, as well as households who has purchased a car in the last 10 years, they probably would not like to switch. In terms of social image, people are essentially incipient stage of CAVs right now. So individuals who are concerned about barriers are including people with disabled population. So they're less likely. Individuals concerned about price, they're less likely. And people, or what are the factors, those are more likely to adopt, meaning here income plays a big role. Annual income of more than 110,000 or so, that people are more inclined to adopt. Then car buyers who are infrequent, meaning they're at a point where they're looking forward to buy a car, which they have not done that in the last 10 years. And individuals who are willing to pay more than 30,000 or so for a conventional car than the ones those are paying 15,000 or less. So those are These are 4 factors which are more likely to adopt. So any bar that is a positive sign are more likely to adopt, and a negative sign less likely to adopt, is what we found out. So we had a PRB paper earlier this year on this, where we present more work, and a journal paper we're hoping would be coming soon on this. In terms of ICLV results, we essentially, this slide summarizes what I just spoke. In terms of high-income households, those are the factors favoring CAV adoption, as well as frequent car buyers, households with high willingness to pay towards conventional vehicles, as well as tech savviness. And hindrances towards CAV adoption is essentially high purchase cost, and somebody who has purchased the car in the last 10 years or so. So there are major challenges as well as some policy interventions towards this. The major challenges includes the costs. And another challenge is that towards barriers, especially at initial stages, people are not confident that the technology will work. In terms of policy interventions, gaining public's trust towards automated technologies remain a challenge. That is why we see a lot of agencies essentially coming up with a lot of studies and advertising techniques, providing the proof, sharing the data. So those are some of the things that we need to overcome. So with that, I would like to conclude the first part of the presentation, which is individual adoption of highly automated technologies. And now we look into organizational adoption of highly automated technologies. The reason it is different for organizations is that organizations do not behave in the same way as individuals, such as individuals might not be willing to take a risk at one point of time, but organizations might want to, because it is associated with their future revenues, as well as an organization's decision is based on a number of individuals which work in a company, as well as the competition that they have with others in their business. So these are the factors essentially which are not considered or not so important for individuals that we need to look into organizations. So looking into organizational adoptions, there are different type of technologies coming. We saw the first 2 presentations about platooning technology. We see transit automated buses. We see for last mile deliveries, drones or various types of last mile delivery robots, those are coming, as well as roadside units, which are public transportation organizations are looking forward to buy and install, such as 3D printing technology vehicles as well. So which organizations are more willing to adopt this type of technologies? And our goal here is to develop a framework, not necessarily kind of forecast, while we focus on one technology for rest of the presentation, but our main goal here is to provide a theoretical foundation for us to move forward. So the left-hand side of the figure we already looked at in terms of individual adoption. Now for organizational adoption, the way it is different is that various types of organizations work in different type of spatial scale, such as organizations work in a very small geography, such as just local. Some, like trucking, for example, they do like long haul versus short haul, or companies who represent just local, regional versus national scale. So the spheres of influence or tendency toward innovations essentially is a concept of scale that we need to incorporate in our analysis. So considering that, we looked into literature. What are the type of organizational adoption that people have done, such as in healthcare? When a new technology comes from IBM, for example, in healthcare, does it adopt it in all hospitals? Or when such type of a computer technology or software comes, does it being adopted in all organizations, or who adopts, who does not? So we looked into more kind of the business related research, or what we call as the organizational theory. 3 things came out of that research is that we need to understand what we call as the entrepreneurial character, business environment, and organizational attributes. I would not go much into detail because there is a lot of material here, but for each of these characteristics, for example, entrepreneurial character, so how a small and medium firm will behave versus how a large firm would behave, it is very drastically different. For example, for a small and medium firm, the decisions are more or less centralized because the firm might have just one headquarter. And the number of employees who are working could be very few, so they can take a decision very quickly. Whereas a large firm, kind of decentralized. They have one headquarter, but many sub-offices. The headquarter cannot make a decision without consulting their sub-offices. Similarly, the gender issue or the gender ratio of male versus female. The age issues of whether the manager is younger or kind of not so younger. What is the education level, average education level of the company? What are their professional network? What are their competition levels? So those are the things essentially we need to look into. And similarly, there are characteristics in terms of business environment as well as organizational attributes. So we try to incorporate these qualities in our approach. So the approach is the same approach that we took in terms of what we did in the organization. The first part of the organizational modeling, here also we took the agent-based modeling approach. Here we, instead of just the adoption survey, here is the organizational adoption survey data we want to consider and construct the social network here. And the way the social network is developed is different than that of the organization. So at the end of it, what happens is that this is a hybrid of agent-based model as well as a choice model. So what we see is that we create the social network, identify peer-to-peer communication and the strength of the peer communication, and utilize that connectedness in the choice model. And the choice model considers both aspects, meaning the characteristics of the responders, what they have responded to, as well as what are the social network or the peer effect is what we say. Those are, both of them are considered, and we kind of compute the parameters using the choice model and finally come up with what are the adoption levels. So what we did was we created a synthetic data set of 500 organizations, and what you see the picture is their social network. So each organization we try to connect to as best as 50 other organizations if possible or less. And the multidimensional space here is a factor of various types of socioeconomic factors of the companies, whether they are going through privatization or public companies, their ownership type, as well as what is the type of business they do in terms of their vehicle running length. So here I'd like to mention that what we're seeing is for highly automated technologies for trucks. That is our kind of analysis that we did, or our specific focus here is truck adoption because we're looking into companies who operate trucks here. So this dimension is a 4-dimension space data, what we see. So the first or the left part of the figure is we see the whole social network, and the right side, we see the social network, how it looks between the organizations. So here, the left-hand side of the figure shows that how the social network essentially looks when there is no peer effect, versus the right-hand side essentially shows with peer effect. So there are 4 colors to look for, is that companies who reject adoption, companies who are willing to test the adoption first or test the technology before adopting, or companies who are doing or going for partial adoption, not full adoption, but part of it and then go for it, or companies or organizations going for full adoption. So that's what we see. At the center, we see the big cluster that is intuitive because the people or the organization which are more or less connected are at the center and their strengths are very well connected. So what we see here is that on the left-hand side of the graph, we see on a 25-year scale, what are those 4 consequences in terms of reject or test or partial adoption or full adoption. In the initial years, we see the percentage of rejection is very, very high, whereas that percentage goes on reducing if the technology is introduced, it is properly advertised, and the technology functions well in the time frame of 25 years. And then that is being decreased. And that is what we see in the bar graph on the left-hand side, as well as the social network on the right-hand side. I think I have taken kind of enough time. And this was kind of my last slide. There are two papers that we have worked on this topic. The left-hand side paper is already published and available. The right-hand side should be available in probably a couple of weeks' time. We just submitted the proof of that. So where we go into much more details in terms of what we have done. So finally, thank you. Before I conclude, I would like to acknowledge all of the agencies who have funded this work at various phases. The first one is our state DOT, Tennessee Department of Transportation, mostly on the individual side. On the organization side, the funding that we have received is from FMRI, the Freight Mobility Research Institute, which is a Tier 1 UTC located at Florida Atlantic University. We have also received local funding from our city, as well as the FedEx Institute, as well as some of our university, part of our university research funding also initiated this work. So with that, I'd like to conclude and happy to take any questions. And I have my contact information here as well in case there are any questions after today's session. Thank you, everyone.
Thank you very much, Dr. Mishra. We certainly appreciate that. So this concludes the presentation portion of our webinar. Now we will start receiving questions from the attendees. Looking at the chat box, I can see many questions. So the first question, it's to all the panelists. Do CAV track platooning stop to DOT wait stations? So any of the panelists could answer this question?
Yeah, this is Samer Disuki. Currently, there is no policies about this because we don't have a full deployment and implementation of platooning, so we can tell whether they have to stop or not. But the current practice, yes, for the trucks that they have to stop to check on the overloading. So we expect that this practice should be continued to be conducted on the platooning as well if such technology is going to be 100% deployed.
Okay, thank you very much, Dr. Disuki. So the second question is to Dr. Hani. Was the trucks assigned to the rightmost lane in the simulation or allowed to switch lanes?
Yes, this is a very good question. In our scenarios, for sure, we have some scenarios where we will have all the trucks are using the most right lane, and in other scenario, some of them are allowed to use other lanes, and this is very important to better evaluate the operational and safety impacts of truck platooning.
Okay, thank you, Dr. Hani. The next question is also for you. Can you highlight why did you use Python, or what did you use? Is it Python, and why?
Yes, we have used Python in VSIM analysis. As you know, you need to use any of the VSIM.com scripting, and this can be done using any of the programming language such as C++, Java, Python, or MATLAB. So we have decided to use Python because my students is more familiar with this programming language.
Okay, thank you, Dr. Hani. I think there's also a question for your presentation. It's asking about slide 15. Does slide 15 represent the network created by VSIM or a picture of the network that was created or that will be created?
Yes, for slides 14 actually and 15, since we have created the whole network in VSIM, so these images are or were created by VSIM.
Okay, thank you, Dr. Hani. The next question is for Dr. Samer. Someone was asking, what is the relation between passes and traversal of a truck? Does one pass correspond to one traversal of a truck?
Yeah, one pass consider a one axle loading pass, because every axle load represents a different loading and could be a different configuration. So we consider a one pass, a one axle pass. I'm not sure if that question to me may be for other speakers, but that's how I consider pass in our finite element modeling.
Okay, thank you very much, Dr. Samer. So the next question is to Dr. Hani. How do you model platooning in VASM? Is it an inbuilt feature or using API?
Okay, actually in fall 2018, VSIM has released a new version, VSIM 11, which contains some specific features for connected vehicle and can be used for truck platooning. So truck platooning can be modeled in VSIM through COM scripting, and this COM scripting is not inbuilt or API features. But through VSIM-COM, the user is able to manipulate the attributes of most of the internal object dynamically. So we have used the Python programming language to script platooning in VSIM.
Okay, so thank you very much, Dr. Hassan. So I see another question for Dr. Hassan. What were the driving behaviors of the passenger vehicles in simulation? More aggressive to attempt to cut between platoon, only asking because of the inter-platoon distance.
This is, it depends on the scenario that you are going to design in complex traffic area like merging and diverging section. You need to use different types of driver behavior, like more aggressive or normal driving behavior, in order to better examine the operational and safety impact on truck platooning at these complex locations.
Okay, I personally have a question for all the panelists. It's about the control level. What was the control level for the truck platooning? Is it level 1 or 2 or 3? Because I think this affects the analysis.
Yeah, this is a very good question. We are following the technology that we have right now, which we assume that the first truck platooning is driven by a human driver, and for the following trucks, they are fully automated. So this is the assumptions that I am using in the simulation analysis.
That's the same assumption for us.
Okay, perfect. So I see a question. I'm not sure if I already went over this question. It was the trucks assigned to the rightmost lane in the simulation, or allowed to switch between lanes? I think Dr. Samer answered this question.
I have answered this question.
Okay. Okay. One question to Dr. Samer. I'm personally asking this question about the effect on the pavement. So we know that the repeated load in the same, assuming that the trucks are following the same path, it affects the rutting. So is there a way to control the path of the trucks just to reduce the impact of the rutting? Dr. Samer, can you hear me?
No, I did not hear the question.
Okay, I was asking a question about the impact of the truck platooning on the rutting. I was asking if there a possibility, or is it even feasible to assign like a controlled movement of the trucks just to reduce the impact of truck platooning on the rutting?
I'm not sure what the technology would do, but if there is a potential to allow a random variation and distribution for the offsets for the following trucks to the leading truck in such a way to make sure that the same point on the pavement is not loaded for 2 consecutive trucks at the same time. If that would be possible to program in the code for the platooning, that would be a potential use to allow these offsets to minimize the impact on the pavement damage. Again, it all can be by programming the code in the platooning to allow such movement if we follow the concept of the leading truck as fully operated by a driver and the rest is completely followed.
Okay, thank you very much, Dr. Samer. So I can see a question to Dr. Mishra. It's, do you believe the pandemic and social distancing will push for more acceptance, adoption of autonomy?
Yeah, very good question. So we cannot say for sure because there is so much of data currently being collected. I'm sure many of you might be receiving a lot of surveys as well. So even though we cannot say conclusively that whether it will increase acceptance or adoption of autonomy, one thing we can say for sure is that when it involves less crowding and less interaction with other individuals, people feel safer in the initial survey results. I will give one example. So if there is a transit or a bus, somebody uses it, and if one sees that there are kind of less number of travelers in the bus and the bus is autonomous, meaning which also has the capability to clean itself after one usage, then people would feel more comfortable utilizing that because there is less number of humans and the kind of seating arrangement is at such, the social distancing is maintained, people would feel more comfortable. So that's essentially utilizing a shared service, for example. In terms of individual adoption, we have to kind of wait and see on, when the surveys are complete and we kind of gather more data and do analysis. But very good question, because the pandemic, what it has resulted is probably, number of changes on how people perceive on travel behavior. So something we will know probably in the future once we gather more data.
Okay, thank you very much, Dr. Mishra. So our last question, it's to any of the panelists. Are the trucks platooning on a dedicated lanes, and how many lanes, and what is the speed? I think it's to Dr. Samer or Dr. Hani.
As I mentioned, yes, go ahead, Dr. Sam.
Yeah, I guess we answered that. A dedicated lane would be the right lane for the platooning, and that's the whole idea for dedicate one lane for it, especially that most of the interstate highway system, which has the massive number of trucks, the most part outside the city limit would be only 2 lanes. So allowing them to move from one lane to another, that's not really complementing the concept of platooning here. So yes, it is one right lane only dedicated for platooning. Dr. Hani, feel free to respond.
Yes, I agree with Dr. Samer. And in addition to that, in complex traffic areas like merging and diverging sections, we are trying to test also other scenario when we allow the truck platooning to use the middle lane to see its effect on merging and diverging in this section. But overall, we are allowing the truck platooning to use most right lane most of the time.